Ever wonder how scientists turn flat photos into detailed 3D models of objects? Today, we're diving into a groundbreaking technique called photometric stereo, a method that uses multiple images with different lighting to reveal the hidden 3D structure of surfaces. But here's the twist. Researchers are now using a revolutionary approach called Gaussian splatting to make this process smarter, faster, and more interpretable. Let's break it down. Photometric stereo has been around for decades. The basic idea is simple. Take the same object under varying light directions and use the way it reflects light to calculate its surface normals, like a 3D map of tiny hill and valley directions. But traditional methods hit a wall. They struggle with tricky materials, shadows, and reflections. Plus, many modern approaches rely on complex neural networks that act like black boxes, making it hard to understand how they work. Now imagine a new tool that combines the best of both worlds, the precision of physics-based models and the power of modern computing. That's where Gaussian splatting comes in. Think of it as a digital canvas, where every point in 3D space is represented by a Gaussian, a mathematical shape that captures color, orientation, and size. These Gaussians aren't just static dots. They're dynamic, adjustable elements that can be optimized to match real-world images. Here's how it works. The system starts by placing these Gaussians throughout a 3D space, like a cloud of tiny, customizable particles. Each Gaussian has properties. Think of them as tiny, glowing marbles with specific colors and orientations. A special rendering engine then projects these Gaussians onto a 2D image, simulating how light would interact with the object. But here's the magic. The process is differentiable, meaning it can learn by adjusting the Gaussians' parameters to minimize the difference between the simulated image and the real one. It's like fine-tuning a model to perfectly match the input photos. What makes this approach groundbreaking? Unlike neural networks that hide their inner workings, Gaussian splatting offers transparency. Researchers can see exactly how each Gaussian contributes to the final 3D reconstruction. Plus, by simplifying the light interaction model, the method handles complex surfaces more reliably. Think of it as a more robust way to decode the light language of an object's surface. But here's the catch. When you try to map surface details like bumps or curves, these 3D particles clash with the flat, 2D nature of actual surfaces. It's like trying to draw a mountain range with a flat ruler. It just doesn't fit. To fix this, researchers like Huang and team force the Gaussians to stick to a flat tangent plane. Think of it as a flexible sheet that molds to the object's shape. By mathematically aligning each particle to this plane, they could accurately calculate surface normals, the invisible arrows that tell us which way a surface is facing. This is key for realistic lighting and shadows. Now here's where it gets tricky. Traditional methods use multiple camera angles to build a 3D model, but what if you only have one photo? That's the challenge in photometric stereo. The solution: place all the Gaussians on a flat, z=0 plane, like a digital canvas, and let the algorithm figure out the 3D shape from light reflections. Each pixel's color is chosen as the brightest highlight across different lighting conditions, like picking the best flashlight to reveal hidden details. The team used a clever two-part scorecard for optimization. First, they measured how well the rendered image matched the real one. Then, they added a normal alignment check, comparing the calculated surface directions to the actual shape. It's like double-checking your map with a compass. Testing on simple shapes and complex objects like a cat or a pot, the method nailed surface details, except where shadows hid the view. Those shadowed areas. They're still a puzzle because the model doesn't yet account for occluded light. But the results are already better than some existing methods, and the best part: this approach is explainable. Unlike black box AI, you can actually see how each Gaussian contributes to the final 3D scene. So what's next? The team wants to tackle shiny materials and tricky shadows using techniques like shadow mapping, which compares light paths to detect hidden areas. Imagine a 3D model that not only looks real, but also behaves like real light. Now that's the future of digital art. This isn't just a technical tweak, it's a shift in how we think about 3D reconstruction. By blending physics-based modeling with modern computational tools, Gaussian splatting opens doors for applications from preserving cultural artifacts to inspecting industrial parts with pinpoint accuracy. And the best part? It's a step toward making AI-driven 3D tech more explainable and accessible. So next time you see a 3D scan, you'll know there's a whole world of math and a few glowing Gaussians behind it. Ever wondered how scientists turn flat photos into detailed 3D models of ancient artifacts or microscopic defects? Let's dive into the clever tricks researchers use to see the hidden geometry of the world, especially when shadows are involved. Shadows aren't just obstacles, they're data. By combining geometry, light, and smart algorithms, we're unlocking new ways to see the world in 3D. And that's just the start of what's possible when science and creativity collide. Thanks for watching. If you want to explore how this tech could shape the future of digital imaging, hit subscribe. Until next time, keep looking at the world and the science behind it with curious eyes.